Hi, good morning. Sorry for a cut, basically, I'll be upfront about this. So the original title of the talk was a deep dive into ICS security. It was still company, shorter talk. So this is kind of a combination of the two. So it'll hopefully give you an insight into what security is in OT and what ICS is. So I would throw that term around a lot, so just give some background to that and the security about that. So a little bit about me. I work as a technical architect in the design of secure systems for operational technology, primarily in air and rail transport. The type of technical talk we had previously on the first round, we're not getting that deep at all, because simply I don't have the skills to do that. So the agenda is what is ICS, pretty standard one. There is some touching on legislation and regulation simply because it kind of needs to be spoken about, but it will be very, very quick. And then about the challenges within security and ICS and those sort of things that are esoteric to that particular or those industries, and then some of the stuff in defense and design, and for the attacking side, which I'm sure many of you will be more interested in. So it is ICS. You'll see these a lot anytime that anyone brings up some slides on ICS. We've got a lot of pipes and some chimneys. My favourite one is anyone in a hard hat pointing at some equipment, although it wasn't until this morning until I noticed that he's quite gently caressing that PLC while hiding an iPad. I don't know what he's doing or why he's doing that, but there we go. So this is kind of what it looks like. It's a lot of sort of industrial type technology. Really, ICS is a blanket term for a whole load of other systems. So this is SCADA or SCADA over here is where you're seeing the high level controls of that. But it's not all factories and power stations. Actually, operational technology covers a whole host of other things. So, everywhere that you see within this building itself, if you came through an airport, if you came through a train station, if you use the roads, all of these things are a whole host of devices that are linked together in some way and managed. So they're kind of one of the main differences between enterprise IT and OT is that the number of people per device. So if you look at a typical airport in the space I work in, you might have well in excess of 1 million end devices with less than 100 people looking at those. So there's that kind of eyes-on to screens that you'll see within, if you work in the banking industry, is you may have like a 2 device per person ratio. It's fact there's a whole load of stuff going on behind the scenes, behind walls, in riser cupboards, in data centers somewhere else. What that means for you, especially if people who want to get into ICS security, because it seems to be a bit of everyone's riding the bow wave at the moment, is that you don't have to go and work in a power station. You don't have to go and work in wastewater distribution, which sounds exciting, but you've got all of these other areas which are managing large amounts of process control systems or distributed control systems or some way that we are looking at what the physical environment looks like. So this is a pretty standard kind of picture that you see. It's taken out of NIST 882 Revision 2. And this kind of shows where you've got this low-level controls down here, some form of actuator or sensor or something that's happening, something managing those, and then you come up to what's called high-level controls. You've got this kind of management layer, and that's where the SCADA servers sit, and people sit up there. So these are out in the field where there is a valve or a pump actuator, that kind of thing. And that's a pretty standard picture to see. It's massive oversimplification of what a control system looks like, whereas this is far more what we're talking about. So these are groups of functional areas within an ICS system and how they communicate. And that's still quite a high level of abstraction. There's a lot of complex systems. And it's worth noting that actually between complex systems and complicated systems are two different things. So a complex system is one in which everything in here, every single interaction or device is generally quite simple and easy to understand. They operate in complex manners. None of it's particularly complicated. It's at what level of abstraction that you enter into. So it all may look sort of untoward at the start, but actually as you kind of pick that apart and pick it apart, you'll understand that a lot of this is actually fairly simple and none so much as the dumb kit. So these are the things that we're seeing. So relays, sensors of some description, an actuator. This is the point where the system is touching the physical world. And so the problem with this, if you're talking about in terms of data security or any form of system security, is that there is no compute capacity in this. I can't have entity authentication. I can't get it to negotiate cipher suites. I can't get it to do anything because it is simply an electrical input and some sort of physical output, or a physical input and electrical output. So that's where our first issue comes in, is that we have no way to authenticate that device or its input. We have kind of trust that the temperature is 37 degrees or the air pressure is whatever it's going to be in millibars. So that's our first issue, inherent trust, which is not an ideal situation. So further up, so this is moving from the low-level controls to the high-level controls. We have PLCs, HMI, which is human machine interface, which you'll see panels on kit around the place, and this is SCADA. So this is a view of the physical system. So we do have some compute capacity at this point. We can do things like encrypt the communications, have entity authentication, but as we said before, that there is we have no authentication on the input to that. So everything here is done on trust that that particular propane tank is not going to blow up. If you look at Mr. Robot when he takes out the data center, and that he is basically fooling the system into thinking that it's a particular temperature. One of the issues with that particular one, I know other people have they've done talks about that particular attack, is that the fact that there are hundreds of thousands of end devices, the fact that trying to fool one is very easy, but trying to do that 500,000 times is a lot of hard work. So it's looking at what the actual risk profile of that is. What is the chance that someone is going to attack all 500,000 end devices? Probably low, so you have some control of risk around that. So all of these devices talk on some proprietary and open source communications. There's an issue here, is that these are all very much plain text. So the simple attack on this is to just intercept that and man in the middle and write whatever you want to write into it. So this one here is Modbus, which is writing a single register, which is out to a PLC and is writing some data into that. There is nothing that's happening in the stack above that is authenticating any of that at all. This is just taking that on trust. And I know I'm sort of hammering that point home, but it is very important to know that. There's a telnet session, and we have DMP3, which is another one. There's a whole host of protocols which simply take that data on trust. That's okay, because you wouldn't put those facing the internet until you have a look at Showdown. And I will admit, so out of those 18,000 systems that are showing BACnet, 502 are Conpot, which is a honeypot. One of the things I've done is some of the slide notes for this. I've created a GitHub repo. There's a link to the end of it, at the end of this, that actually shows you some of this data as well as some of those direct links to that, so you can have a poke around and see what this is doing. So not all of these, actually that's from port 47808, not all of those are BACnet, but enough of them are for you to be a little bit worried about that. So the fun one, legislation and regulation, there's lots. So it depends what industry you work in, and there'll be a whole load of legislation and regulation that doesn't directly apply to security, but will determine what you need to do. So if you look at the nuclear industry, power industries, they've all got their own sets of constraints. You need to just not blindly apply a technical solution to it. It needs to be in context with what the regulators say that you must be doing. So it's a bit like if you're working in PCI DSS world, is they'll make a whole load of policy decisions that you have to abide by, regardless of whether they're correct or not. You can have that fight out with legislators. It's entirely up to you. So you should be aware of them and how they apply to your organization. You're not by yourself there. All of the technical solutions that go into these systems will have the same constraints. So it's a case of understanding where that fits in and which ones apply. So challenges, which I put in, it's a horrible term, challenges, so I put it in italics because it's one of those ones where really it means that why is this so difficult to do all the time? One of the major concerns, especially in areas where if you're looking at power distribution, you're looking at airports, or you're looking at road networks, all of these things have a high operating time. So in the industry that I work in at the moment, we have a 4-hour maintenance window every day. And that's not a 4-hour shutdown. The systems are still running, the facility is still running, but we've got 4 hours in which to make any changes. So things like patching cycles, the reason why we might sit a quarter or half a year behind everyone else's patching cycle is because you can't get to the kit fast enough to upgrade that, or to update that in some way, or to make those kinds of changes. The other factor with maintenance as well is things like physical access to the thing. If you're looking at a North Sea oil rig, then it's all very well saying, I need to replace this bit of kit or I need to update that. It's the fact that you physically have to get to that. Or, you've got long oil pipelines, it's getting to those. So there is a maintenance issue within that. Next one is legacy kit. Is because this maintenance issue means that you are way behind any form of bow wave of stuff that you should be patching, is that all of your kit or replacement of that kit as well goes by the wayside. In fact, I put a couple more slides in here which just show some horror shows. All horror shows. I've got kit that has a runtime of 8 years. So it's been up. It's not been patched. I know this. And here's another wanky term like challenges, which is compensating controls. It's if I'm aware that that kit is not going to be patched, is not going to be powered down, can't be taken out of service, it's not going to be new, then we need to have a look at what the controls are around that. And that's a very sort of auditor term, I'm afraid, and I'm sorry to bring that to a room of actual professionals, but that is unfortunately, the reality of the situation. Next one is systemic complexity, and I touched on this a minute ago around systems, and they reach a point where they become complex, in that the interaction between components is not necessarily difficult to understand, but on such a grand scale that it becomes difficult to do that. So like I say, it's not complicated, because you can build this up to that point where you understand system, but it's what is the capacity of your brain to understand what a 500,000 device system looks like. It's a difficult job, so actually abstraction is your friend here. So you say, I don't need to understand the entire TCP/IP stack to say that that server talks to that device. I just need to understand at this point, that is the interaction that I'm interested in. Obviously, as you get further into some of those sort of designing around and understanding how that works, you'll want to dive into that further. So this is the real kind of unique kind of lecture one on systemic complexity. So it's not, systemic complexity is not solely a security issue, it's a system operation issue. So this has been picked at in great depth, and there are 3 primary kinds of failures that we look at. And the reason why we're talking about failures here, not security directly, is because security, generally in this case, certainly is a case of, it's a factor of the reliability and availability of the system. If I can trust a device is secure and that what it's saying is true, then I can act on that. If I'm not sure that that's true, then that affects whether I trust that and the availability of that input or output or whatever it is. So look at 3 particular types. Cascade failure, I break one thing, so we lose power, then we hit over to UPS. Actually, I've got 4 hours in which to shut everything down or to continue working. That's kind of a knock-on effect. It's a very simple one. Interactive complexity is this is the one where you didn't know that something else was going to break as the result of, we've all done this, where you go in with a change where we're going to patch this particular device, that removes a TLS 1.0 cipher suite off of that, and the monitoring drops out, and you didn't realize. So this is largely, that's a very simple approach to that. Really, it's kind of, I didn't know that thing was going to happen because I did something that I thought was correct. From a security point of view, this is good from an attacker's view because you might not have the view as a defender what is happening further down the line as a result of the loss of this server or any other component has caused the net effect further down the line. And the last one is tight coupling, which I'm not really sure who came up with the term. It's not the best of ones, but what it is the speed at which a failure occurs. And this may be the speed at which a compromise of servers occur during an attack, is that the first time that you notice that server A has been affected or compromised in some way, the attack is way down the line now, and you hadn't noticed. So there's an issue with monitoring and your response to that kind of event. And the last one is really that security is not the biggest concern, which, and once again, I'm aware which audience I'm in, because I'd really like that to be the case, because it makes the battle much easier. Some of the reason why you'll see resistance to putting in additional controls, making any change within the system is because in this list of, this is actually a reduced list of things, from a Dutch researcher who was looking actually at cascade failures, is looking at the origins of threats to particularly national infrastructure. Actually, the only thing in here somewhere is we've got cyber, which is a horrible term, but it is there. It is in amongst a whole number of other things that exist. So when you're trying to sell this as security, you need to be in the context of, if we upgrade that operating system, I don't care, but actually our biggest threat is wear and tear or any of these other things. So generally, safety is king in this, especially in, you're looking at chemical plants, power plants, all these kind of things where there is going to be a major effect of you perhaps shutting down a connection because you thought it looked a bit dodgy. So you need to make sure that any decisions that you do, or any response times, or any delay to a message while you check whether that's true or not, is having an effect on the security, on the safety of the system. So the available and reliable operations come next is really the case of, where I say that security is an element of availability, is that your job there is to ensure the correctness of the system so that it is operating the correct way if it is not that you are aware of this. And that security needs to complement and to support safety and operations. Basically, you are there not as a department of no, but to say this is how we're going to make the system better than it was previously than when we turned up. Generally looking at a lot of these places where up until in the last 10 years, they didn't even have an IT operation. So the fact that you're coming in with security is yet another thing on that. These are the kind of old school engineers who are terrifying and don't care what you do, where the rest of us are quite passionate about it. So understand that it might be a bit of a fight for this, but you need to put on your big diplomacy pants and understand how it's done. So I've been in a comms room where we walked in, and within a rack itself was one desktop PC, and I said, what is this PC? And they said, that's a fire alarm interface. So when that goes off, that's between the fire alarm and the access control system. When the fire alarm goes off, that all of the doors on fire escape routes open, and it's on this desktop PC running XP that's sat there forever. And obviously inside your mind, you're thinking, fuck, this shouldn't be a thing. Why isn't there more than one of them? Why haven't we tested this? But the other point is that you could go around and say, but one of the issues there is that the people who are putting this in, so the engineers who are chucking this in, don't have the same knowledge of security as you do, don't have the same knowledge of IT. So it's at that point, despite the fact that you're screaming internally, your one job is to go, okay, well, what is the requirement? How long do you want this up for? What is the effect of this? So it's to really kind of not berate anyone for doing that unless it's egregious and horrible, but to understand that a lot of the time these decisions are made because they don't have the full picture of security that you do. So it comes to really that selling security may be hard, is that they don't care. And they don't care because they don't know enough. So you have to do a bit of an education program. Why? We're looking at, we shared a load of passwords, and that's the most simple of it. The reason why we don't share passwords is because we want to know which operator did this particular thing. By sharing passwords, that we don't have that audit trail for that. So it's a case of taking what they know and building up on that. So the next one is what does the estate look like? There is no point in you saying we'll implement all these controls and then we'll implement some VLANing, we'll put some firewalls here and there. If you don't know what kit is out there, stealth IT in an enterprise environment happens occasionally. Someone will come in with their own PC and they'll plug it into the network and do something. In engineering, it may well be that, oh, we need a PC to do this thing, or actually I'd like to look at my emails on the shop floor, I'll plug a PC in here, or I don't have Wi-Fi coverage, I'll put in a 4G 4G hub and connect my machine to that, which connects to the rest of the system. And then the relevant threats and risks to the organization is that those things, if you're coming in with, here's all of the controls that we should put in place, which of those are relevant to the organization that you're in. And then the effect of implementing those and how that changes operations. So one of the biggest resistance changes is if you look at, particularly engineering staff seem to have this thing where they will be ingrained in the process that they do. They press button A, then they look at output C, and they do these things. And when you say, oh, actually, before you do that, I'd like you to enter your password here, that is always a fight with them. I know chances are we won't be doing any of that, but it's a case of that once you change their routine, that becomes a horrible, horrible fight. So I do work in design. I don't do pen testing. I don't sit in a SOC. And it's a case of understanding that whatever I do makes the red team's job as hard as possible, but the blue team's job as easy as possible. But it does also mean that, anytime that all of the people here that are doing some red team stuff, they're off doing CTFs, I have no idea how much of that works, simply because I understand that I can use Netcat to receive a shell, but I have to look up a cheat sheet every single time. So bear in mind that my view on this, especially, is coming from in the design side. I'd absolutely love to talk to people who do this in defense and do this in attack, and what are they poking at. So yeah, in the design as well, it's that logical and physical segregation. A lot of this, it's a horrible flat network, and it's simply because what the engineers need is a connection between point A and point B, and you put that in, regardless of whether that's traversing a large geographical area or between system to system that really shouldn't be talking. Coffee machine probably shouldn't be on the engineering network. Those kind of things where to understand, to start to kind of split that up into logical and physical areas within that. There are some, I know I mentioned about regulation legislation. These are outside of these are standards. ISA 62334, which I'm overly familiar with. Once you look at actually the terms within that, they all seem very obvious to you. When I say this is a security in engineering, is a relatively new industry. So although they're all fairly simple to us, let's get up that step first and get basic controls in, get those understood before we go on and do anything flash like the guys from Dark Trace are doing, things like that. There's no point in them doing that if you don't know what's in your site out there. NIST is very, very far, probably the best place to go for some of this information. And then there's ICS A, which is part of the UK's Cyber Defence 6, which is, unfortunately, has been 2 years out of date so far. I had a check this week. It could be better. I'm waiting for them to revisit that. So understand the environment, it's just reiteration of the one above, and consider what is the applicable configs and tools and controls that you're putting in place. You might say, I want a super duper firewall between A and B, and you go, we don't really need that kind of thing. It's working out what things within that are applicable to you. So because you've got 500,000 devices, the only thing they're really doing from your point of view is they're talking to each other. So from a defense point of view, you need to understand what that communication pattern looks like, and what all of these things here. So, who talks in which direction as well. So if you've got a master and slave set of devices, then really I should only be sending writes down and I should be sending reads up. That's the only thing I should see. So if a write is coming from an end device that you weren't expecting it to, that's a red flag for that. Where is this data being aggregated? So where we showed earlier these sensors and those PLCs, basically what we're doing is we're coming from 500,000 devices down to maybe 5,000 PLCs and down to one SCADA system. At what point is that data aggregated? What point are we verifying that that data that's hitting that server or hitting that PLC is correct? So flow, direction, frequency, and volume. Generally within an engineering system, actually chatty is good. We should see constant chatter. It's when things are quiet. So we see this in our SOC, for example. Once that comms drops off and we see that cliff, that is the point where we start to worry. Something's gone terribly wrong. We've lost a link, or nothing's failed over to one side. And what's the expected content? So we had a quick look at what Modbus looks like on the wire. Is that what we expect to see? Is there any exfil that we're seeing out of that? But the engineers that we've already said are idiots when it comes to security. They know this data. They know what good looks like. They know what bad looks like. They know what something fucky is about to happen looks like. So work with them. Don't berate them for not knowing security, because you don't know engineering. I mean, some of you may well do, but invariably you don't. So in detection and action, it's often difficult to see, and I've been in post-mortems that take 3 weeks, 4 weeks to work out what went wrong. We have recovered from the failure of some description, and we're still 4 weeks down the line trying to work out what happened. For that particular one, it was the fact that there was a EMC Isilon shadow copy job running at the same time as the SQL housekeeping. We hadn't realized that those things occurred, and then we were testing failover, which we do after last flight, which is at 12 midnight. those three jobs, sorry, the two jobs and our failover testing was run at exactly the same time. It took us far too long to understand that. So understanding what your communication patterns look like, what's in the estate, gives you at least some understanding of when something is going wrong. Logs, it says good luck up there simply because you've got two issues. One is if you do have a device with some compute capacity, it largely has no storage capacity. So your logs are maybe 10,000 events, but if that's as far as it can go, and that 10,000 events in a failover takes 5 minutes to fill up, you're not going to see anything useful out of that. So the indicators of compromise and isolation, this is not new to any of us here. They don't mean anything. They give us a picture of what's going on. So if you understand what the system looks like in its entirety to some extent, you understand what expected behavior looks like. Once something strange comes in, that's when you know where to start running down that particular rabbit hole. And one other issue, particularly in operation technology and safety instrumented systems, where what I need to happen is that if there is something safety related, such as I need to open those doors in the event of a fire, I don't want that to be delayed by some form of IDS. I don't want that to be connection sniping to happen on that, or automated decisions that will get in the way of that. So to understand where you can do those things and understand where you should not do those things. So from an attacker's point of view, because these systems are complex, the disruption is easy, but a planned and consistent disruption is much harder to understand what the system is doing and how it's doing it. If you're part of the security team for that particular company, is hard enough already. You've got access to the engineers, you've got access to the diagrams, you can work through this, you can test it on the pre-prod environment, should you have one. You can see what that looks like. If you're coming in from the outside, you may have to take wild guesses at this. And so on the plus side is a lot of it is configured for convenience. So because what I need is point A to talk to point B, and the easy way to do that is just have a pipe between point A and point B. It's to look at, once you understand what the environment looks like, is that those things where they're configured for convenience become evidence. But from an attacker's point of view, if you're doing a red team engagement on that, is that chances are it's default, chances are it's a direct line, chances are it doesn't traverse a firewall, all these kind of things. And with that comes inherent trust. So that device that is talking, that's reaching that server, is not based on any authentication. It's just simply that connection. So you could replace that PLC with your own device, or you could session hijack and do what you need to do to say you should talk to me instead. I've got the data that you want. When you get at the SCADA level, there's two things. There's one called loss of control, which means that they will send a command and nothing will happen. And the other one is loss of view, where they will read something and it's not coming back, or that we've changed the output of that and say this device is up. Default hard-coded and common credentials are everywhere. So you can go to ABB or any PLC manufacturer, Schneider, and just say, give me a list of your default passwords, or give me a list of where there's, got access cameras. Access cameras have their admin password, their admin username is always root, and there's no enforcement on the password. So there's no lockout. So you just hammer that until you find it. And everything's in plain text for the most part. There are some other controls or configurations, such as if anybody come across OPC, which is its previous iteration was using DCOM, where you had to have the same account on the machine as the client, and it was horrible. OPC UA, which is the new version, has a whole load of different security controls around that. I've not seen those implemented yet in the wild because it's designed by engineers, and engineers don't get that. It's another education issue. So those attacks on communications, these are taken from the security researcher with the best name, which is Ian Turnipseed. There are a number of attacks that can take place on those, on communications. Interception, to stop that from happening. Interruption, as we hold that message back. Modification and fabrication, self-explanatory. And then the different scenarios that they have is a response injection, which is, it's a bit like the previous talker with we're going to fuzz what's happening here. And try and gain some information from the system they're attacking. The complex one is where we understand what the system looks like, and we want to make it do this particular thing. And then there's the other ones there, which obviously denial of service, an easy one, reconnaissance, which probably should come above complex malicious response injection, but it's to understand what the system looks like. And then all of these devices, not all of these devices, many of them just have firmware, so PLCs will have some firmware on there, which really, if you want to take control of them, we want to understand what they're doing and how they're wired and how they communicate, is to really sort of dig into those. So you can go and buy one. There's ones on eBay. There's Siemens do like an education kit, which includes a S1200, which is uses S7 communication, which is, I don't know if you've read Countdown to Zero or had a look at Stuxnet. That's their baby there. Get a bit of kit out. Check what ports are on there, fuzzy IOs, check for JTAG headers, check for UART, get onto the chip legs and have a look, or remove the flash chips and dump the EEPROM without blowing it. Or the other option is we go onto Siemens, we go and get the firmware and we reverse it from there. This is not the only, I've pulled Siemens into this, this is not the only one that does this. Go and find them, there's lots of them. And really, sorry, I've quite a quick talker, so I realized when I was doing this previously, I got to 45 minutes, we're at 33, and I think we're pretty much done there. What I've done is all of my notes for this and some of the stuff that was added into it, I've created a GitHub repo for that. It's pinned this morning as a top post under that tiny traffic. And also, point to note that I'm part of NetSec Focus, which a couple of guys from here are as well. If you want to come and join us on there, it's just a community for discussing security and getting on with stuff. So that's a bit about it from me. So sorry, it was short and sweet. Were there any questions at all? No, easy one. Oh, sorry.
So, in testing these environments, are you separating them off and having middle test rigs, or the cost associated with managing some?
Okay, so the question was, when we're testing these environments, do we have a separate test rig, and what is the cost of that? And the cost is huge, because what we tend to do so work in critical national infrastructure, at the moment on the site that I'm working on, we have an entire different building in another town in which there is at least one of each of the systems to do that. The cost of running that is about £5 million per year. The cost of putting that up was about £50 million. So yes, we do. So our pre-prod environment looks very nice, and we try and kick the living shit out of it before we put anything in production. Only because that maintenance window is so short, we haven't got time to do a deep dive at that point. I'm quite blessed, I'm aware, with that kind of environment. It doesn't happen very often. Sorry? Sorry, say. Oh, yes. Oh, okay. Yeah, I think anywhere where there's some human risk involved that people tend to like doing in test before we do it in live. Otherwise, YOLO, we'll just get on with it. Is there any other questions? In which case, thank you very much for your time. Really appreciate it. Thank you.